Okay, this is going to be the remainder of section A on this paper, questions 6 to 9. Starting with question 6, which is about triangles. We've got AB and AC, and we've got the angle BAC is 150. So 150 degrees, 2 root 3 for AB, 9, that's a bit longer, isn't it? AC, triangle's going to look something like that. And the first part of the question is to determine BC. So that's this length, which I'll call little a. And it's cosine rule. That's little a, that's little c there, that's little b there. Cosine rule, which is a squared is equal to b squared, c squared minus 2bc cos a. A squared is what we're trying to find. B squared is 9 squared, 2 root 3 squared minus 2 times 9 times 2 root 3 cos 150. At this point, just a little reminder, cos 150 is equal to minus cos 30 degrees. Cos is negative in the second quadrant. So it's negative cos 30. To help you, you can draw yourself a cast diagram like that and say, okay, that would be 150 there. So you can see its sign would be positive, but cos would be negative. So it's negative 30 degrees. Negative cos 30 degrees, which is minus root 3 over 2. So that's going to give me that a squared is equal to 81 plus 2 root 3 squared is 12 minus 2 times 9, so that's times 2, 18, so that's 36 root 3 times root 3 over 2, and that's negative, so that's positive there. Which gives me 81 plus 12 is 93. 36 over 2, 18 again, times 3 is 54, which is 147. So the square root of 147, if you break it down, we know we're told in the question we want it in the form k root 3. So take a root 3 out and we're left with root 49. So that's 7 root 3. Oh, whoops. So that's the first part of that question. The answer is 7 root 3. The next part, it says point D lies on BC and AD is perpendicular to BC. So we've got point D here. Now there's a couple of ways to do this, but the easiest way is to realise that since AD is the height, then we've got a half of BC times AD is going to give us the area of the triangle, because they're perpendicular. It's just half base times height. And then we can use the other formula for height, half AB sine C, to give me half AB times AC times sine of A. They're the same. They're going to give me the same thing. Obviously, we can just ignore the halves. So I can use the fact that BC, I know that, I know that, I know that, I know that. I can work out AD. So BC is, I haven't written it on the diagram, but we just worked it out, it's 7 root 3. So I've got 7 root 3 times AD is equal to AB, which is 2 root 3, times AC, which is 9, times sine of 150, which is a half. So I've got 7 root 3 AD equals 18 times a half, 9 root 3. Just see the root 3's cancel, and we're left with AD is 9/7. So that is that. Those two parts to that question. Okay, question 7. Row reductions. 1, 1, 1, 2, 3, 1, 1, 3, minus 1, 1, 3, lambda. So if we're going to show that we don't have a unique solution, then I've got to perform row reductions until I get rid of one of the rows, basically. So I'm gonna a couple of options. I'm going to add the third row to the first and second. So I'm going to do row 1, add row 2, and I'm going to do row 3. I'm going to go row 2, add row 3. And that gives me no, that's not the best way to do it, is it? Let's think about another way that doesn't involve dealing with so many lambdas. Let's do row 2 minus 2 lots of row 1 to start with. And let's also do row 3 minus row 1. So that'll give me zeros in the first column. So the first row I'm not going to touch. Second one, do this, minus 2 lots of that. So that's 2 minus 2 lots of 1 is 0. 3 minus 2 is 1. 1 minus 2 is minus 1, and 3 minus 2 is 1. And then do this one, minus 2 lots of that. No, minus 1 lot of that. 0, 2, minus 2, lambda minus 1. And you can see already that these two rows are multiples of each other. So in fact, at that point, you could say, since row 2 is a multiple of row 3, row 2 is a multiple of row 3, then what is it? Then there is no unique solution. Some statement equivalent to that. No unique solution. Part B, part 1, says determine the value of lambda for which the system is consistent. So I need to do a little bit more than what I've done there. I'm going to double row 2 from before. 1, 1, 1, 1, 0, 2, minus 2, 2, 0, 2, minus 2, 2 lambda minus 1. So it's consistent if lambda minus 1 is the same as 2, i.e. that lambda equals 3. So So that's that mark. And then it says, for this value of lambda, find the general solution of the system. So part 2, we're going to find the general solution of the system where lambda equals 3. So I'm going to start by pulling out this equation. I've got 2y minus 2z equals 2. And I'm going to use z equals t as my parameter. Don't have to use z, you don't have to use t, as long as you set a parameter, and don't use lambda, obviously. Lambda's already got a use. Just going to confuse yourself. So we've got z equals t. That's one part of my parametrization. Parametrization. It's not a word I'm good at saying. So obviously, can divide that by 1. You get y is equal to 1 plus t. There's the next part of my parametrize. I'm going to look up how to say that word. And then the last one, I can go back to the rows, or I can go back to the original set of equations, x plus y plus z equals 1. That's what I'm going to do. I'm just going to use that one. X plus y plus z equals 1. And I've got that x plus 1 plus t equals 1. So those 1's will cancel. I've got x is equal to minus 2t. Done. Question 8 was not required, but for posterity I'm going to do it anyway. So show that the vectors ABC satisfy the, given that the vectors ABC satisfy this equation, show this. So I'm going to use A plus B plus C equals 0 as my starting point. I'm going to cross product it because my answer's got cross products in. I'm trying to show this. So I'm going to take cross product with A of both sides. A cross A plus B plus C is equal to A cross 0. A cross 0 is obviously still 0. Any vector crossed with 0 is 0. That's kind of the point. On the left, I can use the distributive property. Any vector crossed with itself is 0. So I've got A cross B plus A cross C is equal to 0. Just rearranging that. A cross B equals minus A cross C. And the vector product has this property that if you have a negative and you rearrange, if you change the order, it's not commutative, it's anti-commutative, which is that A minus A cross C is the same as C cross A. So that's half of what we've set out to prove. Just got to add in the last bit, which you do through exactly the same process, but choosing a different vector here. So do the same thing, but with B. Would also work if I did it with C. A plus B plus C equals 0. I'm going to skip a few more steps. This time I've got B cross A. B cross B is obviously 0, plus B cross C equals 0. So B cross C is equal to minus B cross A. B cross C is equal to A cross B. And that's the last part. We already had that was the same as C cross A from above. That's the last part there, done. I haven't written it in the same order, but it's trivial to do so if you feel that kind of pedantry coming on. Okay, the last one, question 9, section A. find an expression for f dashed of x. So I've got f of x is equal to e to the x minus x to the e. Can't read that very well on there, but that's what it's supposed to say. So a part 1, find an expression for f dashed of x. Well, that's nice and easy because e to the x differentiates to itself, and x to the power of anything follows the same rule. E to the x, and the power goes, sorry, e times x, and power goes down by 1. So that's f dashed of x. And then part 2 says, given that that is equal to 0, and it has 2 roots, state what those roots are. If you try and solve this equation algebraically, it can get a bit messy. But what they're expecting you to do is to realise, is to just look at that and realise that you can probably see what the answers are going to be. There's only a few numbers that really you're going to try in your head. And you could try 0. If x is 0, what happens? Well, if x is 0, I get e to the 0 is 1 minus e times 0 to the e minus, well, that's going to be 1. It's not going to be 0. What other numbers might be sensible to try in your heads? 1 would be a sensible one to try. So we get e to the 1 minus e times 1 to the e minus 1, which is obviously just e minus e, which is 0. Oh, look, that means 1's a root. What's the only other sensible number to try in this situation? Well, it's e. So let's see what happens when you do e. E to the e minus e times e to the e minus 1. Well, that's e to the e minus e to the e, which is 0. Oh, look, e is also a root. There's no need really to write that down, as long as you can reach the conclusion that 1 and e are roots of this equation. So that means, what's the sketch of the graph going to look like? So, well, I've got all the information I need for a sketch of a graph, really. I've got that at 0, it's equal to 1. That's what I worked out there. So it starts up here. It's got a minimum, that's e here, and it's got a maximum up here at 1. It's got to look something like that. Move that maximum. Oops. I'm going to move this maximum point so it looks like it's more like there. Something like that. Sketch the graph of f, clearly show the maximum and the minimum. That's done. Hence show that e to the pi is bigger than pi to the e. Hence show that e to the pi is bigger than pi to the e. Well, since e to the x minus x to the e is bigger than 0 for all x bigger than 0, providing x is not equal to e. Obviously, at e, it's equal to 0. So I've got to exclude. If I want to use the strict inequality, then I'm just going to exclude that situation, which means that in general, e to the x is bigger than x to the e, and specifically, pi to the x is bigger than, sorry, e to the pi, get it the right way around, e to the pi, substituting in pi, must be bigger than pi to the e. That's a classic example of the question building towards something that, if it was just stated outright, prove that e to the pi is bigger than pi to the e, would be very difficult to do. But if you use everything that you've learned from the previous parts, it's easy to reach that conclusion.